Okay, everybody, I think we're ready to get going today. My name is not Warren McPhail. My name is Matthias Carlson, and I'm here with a few colleagues, including Curtis Whitson as well in the panel. And I'll be working as a moderator for today's webinar with Warren. Before we start, we're going to go through a few logistical items. The first one is that we have a lot of participants registered for this event, more than 300 actually. So that means that we're using a system called WebEx event, which means that everybody is muted by default. That does not mean that you cannot ask questions. There is a Q&A part in the chat box that you can locate to the right in the WebEx menu, and you can ask questions as we go along. But we'll cover the Q&A questions either at the end of the talk today in the Q&A session, or Warren will follow up with you all over email or LinkedIn or somewhere else after the presentation as well. So we managed to answer all the relevant questions. We've set aside between 45 to 60 minutes for the presentation, and then a Q&A session after that with no hard stop. So we'll simply just go until we have answered at least what we feel are the most important questions. Also worth mentioning is that we will record this session and make it available to everybody after the event. It will also be available on Whitson Academy, which can be accessed on academy.whitson.com for those of you who subscribed to that. And Whitson Academy is simply a place where we have our virtual courses online, topical webinars such as this, also on-demand pre-made courses on how to essentially do different engineering analysis in the petroleum domain, mainly related to the things that we in Whitson work on a day-to-day basis, which is mainly related to PVT, gas EOR, as we'll talk a lot about today, and gas condensate reservoirs. And it's, of course, for all levels, from beginner to very advanced expert. So that's something that where this webinar and other webinars from the past have been also uploaded in addition to many other things. But to set the stage for this webinar today, we thought that we could just review, because the audience is quite wide, so we wanted to just review the most relevant gas EOR schemes for the sake of this discussion today. The different gas EOR schemes that we at least find relevant for today's discussion is gas huff and puff, gas well-to-well double displacement, and then frac-to-frac gas EOR, which we'll talk about today, where there is a continuous or simultaneous version of that, and also a cyclic or asynchronous version of that. And just in short, gas huff and puff is what most companies are doing right now in unconventionals. Well-to-well is what most companies are doing in conventional reservoirs. The continuous frac-to-frac scheme is what Warren is going to present some field pilot results for today, while the cyclic or asynchronous scheme is probably what is going to be recommended going forward from the learnings from the pilot and other simulation work that has been done since then. For those of you who don't know what the huff and puff method is, it is essentially that you go into one of these multi-frac horizontal wells that has been producing for, let's say, 3 years. You go in there and start to inject a gas, many times a associated gas or a natural gas, but also sometimes CO2. You might be injecting for a period of, let's say, 30 days before you potentially shut in the well and let it soak for a period of time, or you just pull it back on production for, let's say, 30 days. So very, very simple. The second option was this well-to-well displacement, which from a surface perspective is exactly the same as what we would do in conventional fields, where you have dedicated injector and producer wells. In unconventionals, this has not been very successful with horizontal wells against horizontal wells because of the very poor volumetric sweep efficiency you get in this type of scheme. For the sake of this discussion, we're going to discuss the so-called frac-to-frac displacement, where you isolate every alternating fracture, either for only production or only injection. And there's two different completions that you can associate with frac-to-frac. The first one is the so-called continuous version or simultaneous version, which is what Warren is going to present field results of today, which requires two tubings downhole, where one of them are only feeding injection gas to the injection fractures, while the other one is only getting produced hydrocarbons from the formation. And you're essentially injecting and producing at the same time all the time in the well. The alternative to that is to, in a similar manner to Huff and Puff, do it in a cyclic way, such that you're injecting for a period of time where only the injection gas is going into the injector fracs with a set of ICDs, can be one-way valves. And then in the production period, you only produce from the production fracs, also then with the opposite type of ICDs that allow for flow only to produce. And that will essentially, at least on paper, be a line drive type of displacement from one fracture, the injection frac, to the producer frac, where there will also be a pressure differential between the fracs, where the highest pressure will be around the injector frac and the lowest pressure would be around the producer frac. So on that note, I hope everybody is a little bit more on the same page in terms of both terminology and what we're going to talk about today. And I would like, with that, to introduce our speaker for today, Warren McPhill, a very good friend of myself and us as a company, and has significant expertise within both advanced completions and EOR. In terms of his career, he started with Imperial Oil before he joined Devon for close to 20 years, before he then the last couple of years have been working in the oil field service sector. The focus that he has had the last decade is extremely unique, and that's why we're very, very fortunate to have him here with us today, where most of the focus has been around, namely, this frac-to-frac gas EOR and associated completions, not only from an operator perspective, but also from a service side perspective. And he was also part of the team that piloted this type of technology for the first time when he was at and with Devon, and Devon has agreed to let Warren share some of these results with us today. So on that note, Warren, I welcome you, and we're very much looking forward to your presentation.
Thank you, Matthias. Yeah, career-wise, I'm currently not with the oilfield services sector. I'm available to consult independently, and that's kind of where we're at for the last few months. So I'm going to share the screen and continue on here. Okay, there you go.
Very good.
Okay.
Perfect.
Yeah. Okay. First of all, I want to express my sincere gratitude to Devon for allowing me to present their data and share with the audience work that I helped lead from about 2010 to 2017. I know from experience that both initiating and sustaining momentum in significant technology development work can be very challenging out in the real world that operators must navigate, especially when those efforts are spread over multiple years of what continues to be a dynamic environment for North American tight oil development. This presentation will amount to a summary of really the first chapter of a story that I think much still remains to be written on. It seems that a few operators today are at least aware of the idea of miscible gas displacement in tight oil, and amongst many of these teams, there's a common view that it has enough potential to be quite interesting from a business standpoint, but as for status, almost all this work seems to be limited to on-paper exercises. Today's field pilot highlights and key takeaways will advance that status and will hopefully give us permission to think a little bolder. So my goal for today is to give the audience an advanced place from which to take some of the next steps. Among several practical takeaways, I'll share 3 important conclusions that I believe support the notion of containment and the absence of premature breakthrough, and therefore the feasibility of gas displacement in tight oil, at least for the tested asset. My initial focus here started with unexpected results from a core flood test that was done with the tight Cardium core sample. It showed us that miscible gas, ethane in this case, could recover almost 90% of the reservoir oil from a core sample at normal injection pressures. This was a few years before we first learned of the early huff and puff work being done, at a time when there was really just limited thought being placed into how to address the universally steep declines we see with tight oil primary production. So we had this interesting observation, but it was essentially at microscopic scale. We had to acknowledge that there would be some risk in trying to extrapolate this result to the field. For example, one concern was that hydraulically fractured horizontal wells would quickly see short circuiting between fractures of adjacent wells, significantly reducing our sweep efficiency. So while this lab observation at microscopic scale was encouraging, the expectation of low aerial displacement efficiency at the field scale certainly wasn't. Other practical considerations included whether we could simply achieve and sustain gas injection at rates that we need for EOR. We ultimately settled on a decision to test interfracture injection and production in the same well. It was pretty clear this could be difficult, but the established wisdom about EOR, the high microscopic efficiency of properly applied miscible gas injection, and the excellent macroscopic efficiency that a line drive flood pattern provides under the right conditions was encouraging. Today, we'll just touch the tip of the iceberg by introducing what has been done in the field and some of the emerging thoughts in this area. I'll share a sample of some simulation work that has recently been done, and we'll introduce the field pilot. I'll review that evidence of containment and the absence of breakthrough. And then finally, we'll share some forward-looking guidance that I hope you find helpful in advancing this opportunity. In some ways, this has all been done before. The idea of displacement between fractures directly follows from what we already know about conventional EOR. The scheme. What we're talking about today. This diagram shows the concept at a high level with injection dedicated hydraulic fractures placed between production fractures. In this case, injection and production are simultaneous. Here we introduce time as a variable. Instead of simultaneous, asynchronously repeating cycles of injection and production are used. Cycles tight oil reservoirs that lets us consider this asynchronous injection and production schedule. Huff and puff. For starters, the target volume for each EOR approach is different. Gas injected by huff and puff can only be expected to enter the near fracture face region of the reservoir. In displacement, which with favorable conditions is designed to traverse the region from the injection to the production fractures. Like Huff and Puff scheme, but as the last couple of slides showed, with differing schedules. From a facility standpoint, it's not at all an inconsequential fact that the schedule for an asynchronous displacement scheme is essentially the same as for Huff and Puff. The Whitson group recently published a piece of work that advanced this area by, among other things, providing a rigorous treatment of the in situ PVT behavior, which respected the different recovery mechanisms that are relevant for Huff and Puff and displacement. This chart from their 2020 IOR paper summarized a comparison of modeled recoveries from Huff and Puff and interfracture miscible gas displacement. The Huff and Puff recovery is shown in blue and asynchronous displacement in red. The now familiar gain with Huff and Puff, so often quoted in the 30 to 70% range, is outperformed substantially by miscible gas displacement between fractures. Just a side note about recovery factors that is definitely not trivial. Huff and Puff incremental recoveries typically reference the primary production recovery. So, for example, a 50% incremental recovery from Huff and Puff really amounts to a 3 to 6% absolute incremental recovery factor. Depending on what the primary factor would be, but typically in the 6 to 12% range even. For the very tight formations where this method seems to have gained some traction. In contrast, fracture to fracture incremental recovery factors can be much higher with favorable reservoir conditions, well spacing, and fracture geometries that encourage uniform and efficient miscible piston-like displacement. With ideal conditions, the greatest influence on recovery factors predicted by the models is actually the simple ratio of fracture length to inner well distance. Here, where adjacent wells are landed in the same producing strata. Or stated more simply, under favorable reservoir conditions and flood conditions, a very high recovery factor may be achievable from the region directly between the fractures. Videos ahead help illustrate this. First of all, the sketch at the top of the slide roughly represents the reservoir model with a 250-foot fracture half length and 40-foot frac height, covering the full vertical extent of the pay. We looked at a number of variables, but the model showed that one of the largest sensitivities for recovery was actually that ratio that describes how much of the modeled reservoir is actually swept between the fractures. So what I mean is this area here. So here's the fracture length, and then this would be the distance, well distance to the midpoint hydraulically between these wells. The simulation was scaled for computational efficiency based on 1/2 of a single wing of an injection fracture and the same for an adjacent production fracture. So for this example, don't read too much into the absolute rate values. It's probably more informative to simply note the contrast between primary and enhanced production and between the two displacement schemes. For today's purpose, which is actually to not to look too deeply into sensitivities, but rather to compare performance between the simultaneous and asynchronous schemes, we chose the permeability, frac spacing, and injection rate shown at the top left. Let's look at the results in the next 2 slides. Here's just a few of the more interesting features from the simultaneous scheme. Injection pressure limitations tend to reduce the injection rate for a time after voidage fill-up, and until the relative perm to gas within the target volume increases. You can see this injection rate reduction relatively early in the scheme. Recoveries can be quite good with displacement, here exceeding the primary recovery incrementally by a multiple of about 2, or about triple the total recovery over the period of this simulation. The video shows the displacement front moving evenly and efficiently, fully traversing the interfracture distance well within the simulation period. This is the asynchronous scheme. All the axes scales are the same as on the last slide, except for injected gas, which is doubled. So in other words, only half of the gas was injected for this case in comparison to the last. This reveals some trade-offs with the simultaneous scheme. Firstly, you can see that although we have fluctuating injection pressures, the peak value is considerably less. The recovery is similar to the simultaneous scheme, but the total injected gas is exactly half. And the produced GOR is substantially reduced. So with the asynchronous scheme, this model suggests that there could be lower compression expense, less gas to purchase, lower differential pressures between the packers, and less gas handling needed in the production facility, all with roughly the same total sales oil volume. This recording shows the displacement still moving efficiently, continuously traversing the interfracture region, even with the periodically fluctuating pressure conditions at each fracture. In an analog to this, think about what happens to a well that gets shut in. What happens in the formation? For an injector, well, the pressure continues to decline while the gas expands into the reservoir. So the reservoir sees injection, while at surface there's none. Likewise, for a producer, when shut in at surface, production fluids continue to flow into the near wellbore porosity and fracture system and into the well if they could. So in both cases, what the formation sees is injection and production that continues for some time after the well gets shut in. This differential pressure continuously exists between the I zones and P zones. One final observation. In this comparison, the oil was recovered faster with the simultaneous scheme, suggesting an opportunity for the asynchronous schedule to be optimized here. Here are some key takeaways from the simulation work. In comparing the continuous and asynchronous displacement schemes, gas utilization with less injection gas needed for the asynchronous scheme, the gas purchase cost, compression capacity, and injection facility allocation are all positively affected. For the produced gas-oil ratio, less gas handling at surface and less gas and less recycled dedicated compression should reduce facility-related OPEX. Lower produced gas from the production fractures should prevent competition with reservoir oil for tubing outflow capacity. The injection pressure reduction may translate to reduced facility pressure ratings, but perhaps a more likely result is that wear and tear on packers, a critical sealing element of the downhole system, will reduce. Now, remembering this was a comparative simulation, it may be that with a more cash flow optimized asynchronous schedule, we would choose to boost the injection rates, thus reducing the injection period. These are all points for optimization. And all of these asynchronous benefits come with about the same uplift between the schemes. Finally, the model certainly showed the simultaneous scheme to have a more aggressive early recovery profile, but the main objective of this exercise was to look at an apples-to-apples comparison with equivalent injection rates. These results are starting point. Thinking of the available injection pressure window, there's probably lots of room to look at a more cash flow optimized schedule. Now back to that field pilot. We considered many different factors that might impact the feasibility of fracture-to-fracture gas EOR. From a reservoir and well standpoint, most of the concerns in one way or another boiled down to short-circuiting between injection and production zones, whether through the reservoir or even within the wellbore. So we made design choices, like opting for less treatment-induced fracture complexity and drilling a new and fit-for-purpose pilot well in an underdeveloped area. We selected a formation that minimized the heterogeneity risk and that had moderate permeability in order to encourage a timely EOR response while reducing the risk of early breakthrough with larger frac spacing in a field-scale proof of concept. Beyond these factors, the front-end work was substantial, but really in no way different than any properly designed light oil EOR project. Significant reservoir characterization was done to allow an earth model and reservoir simulation to be built, which was calibrated with a gas injection test from a dedicated test well, relative perm and core flood tests, PVT characterization, and enriched gas, field gas miscibility tests. Finally, knowing our feedstock properties and required plant output conditions, we designed a pilot-scale miscible gas injection facility, conducted the HAZOP, refined the facility design, and worked towards getting the state regulators' approval. Organizing these task dependencies within the overall timeline took a good deal of effort from a dedicated project manager. Thank you, Ryan. These core flood test results are from the pilot area. I think this example helps underscore the importance of using data from the pilot area to establish each of the inputs that I just mentioned. You can see that here we had less than the 90% recovery factor of the cardium test, but good results nonetheless. And within a single injected pore volume, about the same results. You can also clearly see the difference in microscopic displacement efficiency between the immiscible and miscible tests. We chose to test the simultaneous injection and production scheme. This was driven by the intuitive feeling that simultaneous injection would provide superior recovery, the perceived operational practicality of managing the well at steady state conditions, and simply stated, what we could build with off-the-shelf 2013 technology. Injection gas was conveyed down a parallel coiled tubing string and into the annulus below a packer, which is not shown here. The I zones, labeled with even numbers, were manifolded together and set up to fluidly bypass the P zones. Production fluids entered the tubing through a sliding sleeve at each P zone. The zones were isolated from each other using the cemented casing and swell packers. As it turned out, the swell packers in this application gave us a great deal of difficulty. We'll talk more about this soon. Permanent downhole gauges collected pressure and temperature continuously from each P zone and from the manifolded I zones. And optic fibers on the outside of the tubing collected more data along the full length of the completion. This design was intended to accomplish our pilot objectives and wasn't necessarily what we thought would be built for a commercial application. Also, as I said earlier, this is essentially what could be built when the pilot was planned, without introducing the complexity of an intelligent completion of 13 zones or committing to an ongoing periodic well intervention program. I think that today we're in a different place as far as options go. The modeling work I just showed, as well as other work that is currently being published, shows the potential value of properly incorporating time as a variable in this form of enhanced recovery. The next 3 slides will present some of the results from this pilot, and I will draw your attention to 3 important observations that foretell the viability of this EOR method. These charts cover an 800-day period, including primary production, the EOR pilot, and the early post-EOR production. Highlighting only a few interesting features, the top section shows injection and production pressures that noticeably diverge as injection and production independently progress in the segregated zones. The second EOR period is here magnified for clarity. As shown in the middle chart, you can see we had intermittent injection and production throughout the pilot. initially while commissioning the new facility, and then while addressing various leaks we had within the system. Now, I want to draw your focus to two important observations. Firstly, we had 3 swell packer failures during the pilot, each occurring at a different time. They appear as the sudden equalization of injection and production pressure, highlighted here by the X's that end periods 1, 2, and 4. This was, of course, unfortunate, but it did provide an opportunity to evaluate containment, which I'll explore in the next slide. And secondly, the bottom chart shows production rates throughout the pilot. Again, gas is shown in red. It's clear from this chart that there was no evidence indicating premature gas breakthrough. This was after a cumulative 285 days of sustained differential pressure, which included 53 days of gas injection. Just under 20 million standard cubic feet of gas was injected during the pilot, which on a reservoir barrel equivalent basis really isn't that much, but from a reservoir risk standpoint, containment of injection fluids near the well and no early breakthrough were two of the most important reservoir-related items that this pilot demonstrated. Now let's look at that containment evidence in a little more detail. The bars indicate volume, and the line indicates pressure. For each stage, I've converted all volumes of injected gas and produced fluids into reservoir barrels. The relationship between net fluid volumes removed from or replaced in the reservoir at each stage can then be compared with the average reservoir pressure at the end of each stage. This analysis was enabled only because with each swell packer breach, we saw a sudden equalization of pressures between the injection zones and production zones. The quasi-stabilized pressure after each failure provided a good snapshot of the average reservoir pressure in the vicinity of the pilot well. The fact that the relationship between the net change in fluid volume and the average scheme pressure was directly coupled spoke to the high quality of containment. If the injected gas was leaving the system, you would not expect this clear relationship. Now, combining this indication of containment with the evidence I just showed that there was no observable injection gas breakthrough is significant. Think about each barrel of gas that gets injected. If it doesn't break through somewhere or get lost from the system, it can only be displacing a barrel of oil somewhere. Here we focus in to show just period 4. This 15-day scale provides a good snapshot of some important dynamics, with some of the more relevant observations noted in the margin. For context, at this point, we were producing from only 3 zones, with the remaining 4 P zones closed to the production tubing but open to the formation. On the top chart, you can see the gold-colored curve tracking the production pressure for the 3 open and producing zones. I'll show them to you here. Right here. There are in fact 3 gauges here, but at this scale, they're pressure data overlay. PVT analysis told us that the bubble point was close to 800 psi. So here's our bubble point. Right on there somewhere. And you can indeed see the onset of a fluctuating bottom hole flowing pressure below this level. The well's heel down orientation provided a trap for free gas to accumulate and then unload periodically. The top group of pressure data represent 2 sets of zones. Firstly, the injection pressure for the collective group of injection zones is in blue. Closely tracking this group are 2 other traces, representing 2 of the closed P zones. These 2 zones had endured swell packer failures, And because they were now closed to the tubing, they were physically isolated from the production side, but still clearly sensing the injection pressure through the breached packers. Finally, a third group of pressure data represents a couple of P zones that were also closed to the tubing, but that didn't have packer failures. Being open to their hydraulic fractures, these closed P zones each provided a good sense of the pressure support provided while injecting into their adjacent I zones. The middle chart shows the field gas and condensate injection rates. It's easiest to focus on the rich gas curve here, shown in purple, which is just the combination of these two rates. We see a period of low gas injection rates, followed by a shut-in, and then a period with higher gas injection rates. You can see the injection pressures responding to the injection rate changes, and the production pressure buildup while shut in with the loss of lift gas. These observations paint a picture of what's happening on a zone-by-zone basis, but the next observation is probably the most significant as far as understanding the viability of frac-to-frac gas displacement, at least in this reservoir. And this is the third important observation, further supporting the notion that we did have containment near the pilot well. The declining injection rate with a relatively stable, there we go. So the declining injection rate with a relatively stable injection pressure above the original reservoir pressure and approaching the maximum specified injection pressure was as expected as the injection zone porosity approached fill-up. This observation correlated well with the simulation work. Refreshing the most significant observations from the last three slides, we had the demonstration of injection energy conservation, and now a decline in the injection rate while we approach the maximum injection pressure, both supporting the conclusion of positive containment, and finally, the absence of premature gas breakthrough. So the injected gas seems to be staying where it can do some good for this well and not breaking through prematurely. This figure is from a journal article that will soon be publishing. These authors compared Huff and Puff with both displacement schemes and explored several sensitivities that may drive asynchronous displacement performance. In these next two slides, two sensitivities are highlighted which seem to me most relevant to the selection of a next potential pilot area. First off, to contrast this with the earlier simulation work, the high incremental recovery factors in these examples are largely an artifact of how the simulation boundaries were defined. Recall the nature of the relationship between the modeled boundary and frac wing length. So far, practically all the published work has been based on rather tight permeabilities. In this example, a base case of 1 microdarcy was used. Here, we see a clear increase in the recovery factor with higher permeabilities. The case 1 and 2 perms are more like what we might expect to see in some of the more permeable Montney and tighter Cardium examples here in Alberta, as well as some formations in the Powder River Basin and perhaps even the upper tight strata of the Delaware and Midland basins. We also see a substantial acceleration of recovery with the higher perms. This next chart shows the effect of incorporating secondary fractures, which could be natural or hydraulic fracture induced. Perhaps a bit counterintuitive, but here we see an improved recovery factor with all the secondary fracturing cases. Again, keep in mind the base case is 1 microdarcy for this example. I wouldn't expect these sensitivities are additive, but they are helpful in suggesting that there may be opportunity in both tight to low perm sand matrix and very low perm, but natural or complex fractured mudstones. These recommendations offer some of my thoughts about what should be feasible at this point. This is based on the field pilot work presented today, but also a couple of well injection tests that I didn't talk about, and a considerable amount of reservoir and fracture characterization and simulation work that I've participated in. Consider this in the context of a next field pilot rather than a commercial scheme. Clearly, we don't have enough time to talk about each item today, and I'm sure this list isn't complete anyhow. This guidance directs us towards a system that should be much easier to scale up, that should provide just about as good recovery and better economics than the simultaneous system reviewed today. These recommendations resulted from considering economic factors, short-circuit risks, and construction and operational viability at scale, and are intended to increase the likelihood of obtaining a conclusive pilot test. Finally, some items may be important from a logistics or regulatory standpoint, which, if not properly addressed with sufficient lead time, may cause undue delays or even disqualify a potential pilot candidate. For everyone's benefit, I've tried to reduce the guidance to just a few key takeaway points. Here they are. Again, here and on the last slide, these points are really intended to help the audience think about what a next field pilot might look like. This scheme may indeed be quite feasible in tighter permeabilities, but with this guidance, you should find that you're looking at designs with manageable stage spacing, achievable and repeatable completion installations, and suitable injectivity, all while respecting the risk of near-well short-circuiting. This concludes my presentation. My sincere thanks to Whitson for today's invitation, and to Drs. Bamanish and Hamdi from the Tight Oil Consortium for their work on the simulations that we viewed. I would also like to thank everyone that contributed on this project at Devon. And as a final acknowledgement, this wouldn't have been possible without the consent of Devon Energy, for which I'm grateful. I would now be happy to answer any questions that the group might have.
Great there, Warren. Very, very good. Good on time as well. Perfect timing. There's come in a wide range of questions, and I've written them down here, and we'll try to tackle at least the most relevant questions that I think you/we will be able to answer. One question that comes up many times when we talk about this particular technology is this I guess people being essentially afraid of the short-circuiting potential issue, that if there is either a bad cement or if there's a conductive frac from one to another, that all the gas you inject in one frac will essentially this short circuit to the other frac, and the scheme will not be successful. And I think you and everybody, at least on the Whitson side, that's been working on this for many years now, I think I've gotten that as one of the biggest first questions and kind of risks associated to this. So I guess the first question would be to you, and I also would like Curtis's thoughts on that before we go into the specific questions. And many questions are on that topic. So maybe we can just start with Curtis, and then I'll give the word back to you, Warren, and then we'll take the last questions.
Okay.
Yeah, thanks. This is definitely the first red flag question that comes up pretty much every time I've been presenting this approach in the past 5 or 10 years. So for the cyclic process, the short circuiting is a considerably smaller problem than in the continuous. And the reason for that is if you have short circuits, they're typically small volume conduits. Could be bad cement, could be secondary fractures, whatever it might be, are relatively small volumes. And the fact that you're not producing while you're injecting means that the injection is going to fill up those small conduits very rapidly. And then that additional gas that you're injecting will be pushing into the rock, pushing that oil in the rock towards the producer fracs. So that's, I think, perhaps the most important consideration for that. Yeah, I think that's
From,
yeah.
from my perspective, there's a big difference here between the simultaneous and the asynchronous schemes. With the simultaneous injection and production, you're always injecting and of course producing at the same time. So you have these pressure sinks that exist combined with the conduits that tends to equal bad things, right? It tends to equal immediately producing back the gas that you inject in the worst case. So it's a risk. There's a real natural mitigation that happens here with the asynchronous scheme, and that's because the production, those pressure sinks are closed, right? Because the production valves are closed. So what should happen in that case is you essentially fill up that fast flow pathway or conduit short circuit. Let's just call it a short circuit. You fill that up and you pressurize, and if you might pressurize the production fracture, you should certainly pressurize the channel or the short circuit, pardon me, and of course pressurize the injection fracture. But it should take a relatively small volume of gas to do that, and then the rest of the gas is working, right? It's working in the part of the system that has isolation, and that means it's displacing.
Very good. So the first thing, so that was kind of the biggest red flag. We got a lot of questions here, and I'll try to now jump a little bit over to a couple of them that are maybe a little bit more operational to you, Warren. Does that sound okay?
Okay.
The first question would be with regards to when you have two tubings down there in the for the continuous scheme that you were running in this pilot. Do you know the dimensions of those tubings?
Yeah, in the continuous pilot, here we had 5.5-inch casing. I'm just going to pull up that image as well. There you go. 5.5-inch casing, and that was run as a long string, but it crossed over to 7-inch. I don't show it here, but it crosses over to 7-inch as we approach the kickoff point. And that allowed us to run 2 3/8 tubing in here. And this bypass was actually built with a couple of tubes. And that was because of the friction pressure drop that I calculated that we'd see here, right? So we had a couple of 5/8-inch tubes that were on the outside of 2 3/8 tubing, all running through, swell packers to provide that isolation. Now back towards the heel of the well, of course, we had an injection packer, and we delivered the gas to the annulus here via a coiled tubing string, like I mentioned, and I think it was 1.25 inches, might have been 1.5 inches. I don't recall off the top of my head. And that was on the outside of 2 7/8 tubing up in the vertical section. These were just regular sliding sleeves.
Very good. Very good. The second would be related to the downhole gauge pressure locations. And do you monitor downhole injection pressures in the I zones separately from the production zones, or how is that done in practice? Can you shed a little bit more light on that?
In this case, now, let me just say a note on instrumentation before I answer that, which is all of that need for this fancy instrumentation. I think it largely goes away, maybe entirely goes away if you deal with the asynchronous system. Now, that said, and that's of course because of this natural mitigation, because that would be a big motivation for putting this stuff in there, is to understand what's going on downhole, like we did here, right? So now, that said, we had permanent, not drawn here, but each of these P-zone assemblies had a permanent downhole gauge in the annulus that was sitting just outside the tubing and sensing the annulus pressure. And then the injection pressure These two sort of black boxes back here at the end are intended to be pressure gauges, right? So one of them was sensing the annulus pressure, and of course the annulus pressure, because everything's manifolded, represents the injection pressure.
Okay, very good. Do you know any work that has been done to characterize the short circuits, specifically the variation in effective perm and the change over the lives? Well, that's a question from John.
Yeah, there's a fantastic paper that is, it's going to be published, I would say, imminently, and it's this one here. So these authors have a paper that focuses on the contrast. It focuses on a few things, right? But a big part of it is addressing that characterization of how these schemes, both the simultaneous and the asynchronous scheme, would behave with short circuits. And some bonus material here. So we talked our way through this one already, right? This is the wrong one. Here's an interesting one. So here we have the simultaneous injection going into the with the injection fractures in red and the production fractures in green, and everything's open. So you're injecting, and ideally you want your injection gas to traverse this region between the fractures. But if you have a short circuit, and in this case, the short circuit is shown between adjacent wells, which could be a possibility, is a possibility. Then here you have your injection gas going in here and coming right back at you on well number 2. In the asynchronous version of this, your P-zone valve is closed. So when that happens, your injection gas, it fills up your short circuit and this production fracture, but after that, you pressurize the system, and at some point you should fill that up and then reestablish your displacement between fractures. And by the way, when you come around to reopening this valve later on, you should expect some sort of sort of huff and puff style benefit here.
Very good. Very good. A little bit more on that. So the question from Jesse Powell. Thanks for sharing your story. Can you please explain your point on slide 24? GR uplift. So comment on the comparison between simultaneous and the asynchronous.
Yes, okay.
GR uplift, the GR uplift comment on 24.
Okay, so that's where I'm saying the onset of the GOR increases is delayed. So generally speaking, what we see with the asynchronous, so we got to go back. Here's your gas oil shield. Right? This, I probably can't see that. Just a sec. So here's your GOR right there. And here's where it starts to increase. And here's the level that you finally get to. And also relevant here is your total gas injected right here. So in this case, it looks like we have 50 million standard cubic feet of gas injected. And we have this GOR. Same scale, so it'll be easy when I flip it back, of somewhere below 10, it looks like. All right, let's go back a page. That's the asynchronous scheme. Okay, look at this, right? It starts earlier, increases to a higher value, and that's because you have this continuous injection. Let me go back to our rate. Here's our injection rate, 120 MCF per day per frac. Okay. So there's more gas going in because you're continuously injecting. And in this comparison, okay, for these injection periods, as we modeled it, we have 30 days of injection and 30 days of production. So the math is pretty straightforward. You're just injecting for half the time. Therefore, you have about half the injection gas in. And you also see this pretty huge benefit, actually, of more efficient use of that gas. There you go.
Very good. So there's a lot of questions coming in on whether we'll also share the slides and the recording, and of course we'll send that out to all the participants, both over email and it will be available on LinkedIn as well. Curtis, are you still there?
Yes.
Yeah, perfect. So this is a question from Naji, our friend from Hess. So a few questions here. Some of them are we've tried to answer, but the first one that I wanted to touch base on with regards to miscibility. So if the gas is not first contact miscible, how would multi-contact miscibility be relevant in this case? And is that miscibility highly localized? So I guess with that, if you can shed a little bit light on kind of the differences between miscibility in the context of frac to frac, or like a displacement process, and maybe versus what's more relevant for huff and puff, for instance.
Well, this is clearly a conventional displacement process from injection frac to the producing frac. So it's conventional displacement. And if the pressure at the miscible front is above the MMP, then you'll achieve miscibility at the front. If you look at the simulations in detail, they're not shown here, but if you look at the pressure profile between the injecting frac and the producing frac, what you'll see is that you have a very shallow pressure gradient from the injection point to the front. Basically, it's only gas flowing, so the viscosity is lower. And you have most of the pressure drop is from the front on the oil side to the producer. So you actually have a very attractive way to maintain miscibility. In other words, the injection pressure needs to only be some hundreds of psi greater than the MMP to achieve basically miscibility almost the entire way to breakthrough. So it's conventional displacement. Yes, you would generally target for a miscible displacement, but as you know, Naji, even if you're a few hundred psi below the MMP at the front, you're still getting a very high microscopic recovery efficiency. So. Matthias, could you all hear me, or was I talking to myself?
Yeah, I heard it, Curtis. Very, very good. I was trying to find my unmute button here, but very good. The question to you, Warren, would be a follow-up to this one, I guess. If you could do something different in the next pilot, would you recommend fewer injection production zones compared to the one you had now to avoid potential failures, or would there be something else in terms of, for instance, picking packers that you would recommend for the next pilot?
Okay, two parts to that, it sounds like. And I think the answer is kind of specific, because in some formations, for example, if I have higher permeability, it's pretty easy for me. And by higher permeability, I mean, I don't know, half a millidarcy, maybe even 100 microdarcies to 500 microdarcies. And in that case, based on the modeling I've done or seen, worked with, you're going to land on something like 10 to 30 zones, which I'm pretty comfortable with. Yeah, today. But it'll look different, of course, than that simultaneous well that we just highlighted here. It's going to have packers that I'm comfortable with for sealing, and I think there's better choices there, and also not just this ability for them to seal, but also to run into the toe of the well through whatever debris might be there, and uncertainty there might be as far as frac positioning. Like some of that goes away if we have a whole bunch of it goes away actually if we have sleeves instead of perforations in the well. Yeah, I feel like there's some risk of me rambling here, but that is why I put this guidance in here, right? It does capture, I think, sort of my off the top of my head thoughts on what a next, what would help out a next pilot. There was a second part to that question, Matthias. Can you help me out there?
The second part was essentially if that was something, I guess fewer stages was something you would do, or if there was something else that you would do differently in the next pilot. But I think you answered it pretty well.
Okay.
Just quickly in terms of gas injection composition, Anne is wondering about what was used, if there was a lean gas or a rich gas, or if you did any enrichment there, or can you shed some light on that?
Yes, and yes is the answer. So what we had here in the field, as far as the field pilot was concerned, was a miscible field gas, and we achieved that by blending condensate with field gas that we had, obtained from the local gathering system. And we knew that was miscible based on PVT work and lab testing that we had done at pressures that we were, miscible pressure that we were quite comfortable with. Yeah. Around I think 22 or 2200 psi in this case, a little more than that maybe.
Very good.
But that brings up a related point, right? Is your minimum miscibility pressure, multi-contact, needs to be comfortably below your maximum injection pressure, and you would define that by where you expect to have some grief from, opening up natural fractures or hydraulic fractures between wells. So you want to have a comfortable window there.
Yep. Good. A little bit more on the practical aspects. We got a very good question here regarding, this was a long project. That's Devon. Can you comment a little bit more on the science in terms of additional lab work or planning? How many people was involved and whatnot to get this in the field? And that's a question from Andres.
Well, we had a core team that was quite involved on a daily basis. And that was about, it varied, but it was between 2 and 4 people, maybe 5 people, I would say, over the course of probably 3 years. That includes the front end planning and the actual field pilot, planning, everything that happened until we started injecting gas, basically. Surrounding that, I would say we had a group of a few dozen that were, very helpful in understanding, the workings of the particular asset that we had here, and the business side of this, and regulatory, and all kinds of stuff. But at the end of the day, the real consideration here, I think, for operators now is that we've built organizations around, efficient primary production. But the answer to that question that was just asked really is no different for a company that, does EOR. There's no surprises there, right? Somebody has to do the facilities design. Somebody has to, make the regulatory applications and manage this thing while it's running, right? You don't just turn it on and walk away from it.
Yeah, very good. We got a couple of questions related to potential use of foam from both Pramod and Cesar. So if the conformance issue is a big potential issue, could, for instance, use of foam-assisted gas injection be useful here? And potential differences between synchronous and continuous in your head, Warren?
I'm not, because of the natural mitigating effect here of the asynchronous scheme. I'm not too concerned about having to use anything to assist its efficiency. From the simultaneous standpoint, I suppose there could be some help there, but I'm envisioning short circuits that are very permeable, and I would be exposing them. Think about the differential pressures. I would be exposing them to maybe, I'm going to pick a number out of the air because it really depends on your asset, right? But I'm going to pick 4,000 PSI on the injection side and 500 PSI on the production side, and they're pretty close to each other. They're like 50 or 60 feet apart in a pretty densely completed well. So I don't know. I don't think the phone's going to work in that case. Just off the cuff.
Yeah, that's just honest. Yeah, I think we've started to cover quite a few of these questions here. We also have a question from. There's so many questions here. I'm trying to just figure out what surface equipment changes would be needed to retrofit a huff and puff system to a synchronous scheme, and what's the cost impact to a project due to surface equipment changes? Curtis has mentioned many times that if you do a huff and puff first, a lot of the surface equipment is very similar to this, at least on the surface, and you need some additional jewelry there. Would you like to comment on that, Warren?
Yeah, my answer is pretty short. I think that it's, just bringing back this slide here to answer this. I think it's practically the same. I really do. Because you've, for huff and puff, of course, you've set up this ability to be able to inject and then produce and just repeat that cycle. That's all you're doing with this asynchronous scheme on the surface. The difference is downhole.
Yeah. Very good. And I guess from that, there's a lot of details regarding potential details of the modeling work. For the modeling work, I would present it here. I would recommend the people interested in that to maybe contact the TOC group out of UFC, right, Warren, to ask about some more details about that.
Absolutely. Just shoot me an email and I can hook you up with those guys. Happy to do that.
The last question I think we'll cover here, and then we'll, everybody else can follow up with Warren on both his email or over phone. That's given on the end of these slides here. Also after the webinar, I think the last question we'll try to cover is a question from Ashkan, and the potential, I guess, incorporation of doing a refrac in the space of frac to frac or both cyclic and synchronous. Would you see that fit into that space, or is that a different discussion?
Well, I hope I answer this the right way. But a refrac before retrofitting the well, I think it's fine as far as from the standpoint of the EOR scheme. The risk that it introduces is there's more frac time and more wear and tear on the casing, after which you would want to come along and install a completion into. So that's something you're going to have to manage.
Yeah. Very good. And I guess just to clarify, there's essentially a little bit different type of simulation work shown here. So a lot of the questions that have been coming in has been related to these videos that you showed, Warren, and those are done by Hamid Bemenesh out of UFC. And you also showed some simulation work from Stian Midland out of our group here at Whitson. And then you also showed some results on the short circuiting, which was out of the University of Houston, if I'm correct, right?
That is right. OSU and UH together. Yeah. Dr. Lau's the primary author there.
Very good. Very good. So I think on that note, we'll end this session today.
And Dr. Nicolau and Economides from UH.
Very good.
Sorry.
So I think on that note, we'll end the session to today, and thank everybody for showing up and participating with both questions and comments. And I wish you all a good rest of the week, and I guess also Merry Christmas and Happy New Year when that time comes around.
Okay, thanks very much.
Thanks, Warren. Thanks, everybody.